So today we are going to finish this clipping and culling slides, and we are going to see a polygon clipping algorithm. Um, so last time we have talked about Liam-Barsk algorithm, but I just want to state something about both of these algorithms, both Cohen-Sutherland and this Liam-Barsk algorithm. The main goal here is to optimize, to have as efficient as possible line clipping. In terms of correctness, you could have designed a different algorithm which works just as same, because we're just finding intersection points of a line with a horizontal line or vertical line, so the clipping boundaries. That's something very simple, right? In terms of mathematically, if you write the equations, it's not going to be difficult. We're just, for example, finding these t values, the intersection points of our lines with all of the clipping boundaries, is just one operation. But in computer graphics, all of these, a line can be clipped against the clipping boundary in one operation. If you look at the asymptotic complexity, it's a constant time operation. But in computer graphics, we are not, and if you have n lines, we are going to be doing this in O(n) time, a linear time. We are not looking for some sublinear solutions for when we have multiple lines. The only sublinear solution you can have is to have like some kind of a bounding volume hierarchy. So that may be a good way to do, actually, to clip out, to cull certain parts of the scene immediately if they are, for example, within some bounding volume. This could also be done, but if you just consider just those, you have your simple primitives lines, you have a set of lines. I don't think there's an algorithm that can achieve better than O(n) time. Which means that for each of those lines, for a single line, it takes O(1) time to just clip it, because there are a constant number of boundaries, 4 or 6 in 3 dimensions, and finding these intersections. You are doing constant number of operations. If you look at this one here, or if you have written a more inefficient version of this, it will still be O(1) time. But in computer graphics, the important thing is to reduce the constant factors in your big O complexity. It's O(1) time, but if you look at the constants in these running times, you're going to see that even turning, for example, a floating point division into an integer division, or turning your divisions into additions, subtractions. Integer addition and subtraction is more efficient than floating point division, for example, or avoiding, for example, trigonometric functions, avoiding square roots. These things are really crucial in computer graphics. So if we can achieve the exact same result with less number of faster operations, this will give you huge performance boost in your computer graphics application. So in Liam-Barsk algorithm, if you look at this, we are not actually computing those T1, T2, T3, T4. Our line, when we are clipping a line segment, for example, we find the intersection of, we said that we are using parametric line equation and its intersection with the 4 clipping boundaries T, let's call them TL, left, TR, TB, TT, T bottom, T top. The T values where our line segment intersect with these 4 clipping boundaries. You can just find those and then sort them and see, only use the ones that are between 0 and 1, and sort them in such a way that find the interval that is smallest, which will be in your clipping window. But such a case will try to find intersection points beforehand. Do all these multiplications. In order to find this intersection point, as you can see, we are doing a multiplication. Numerator divided by denominator. Here, aren't we doing, in Liam-Barsk algorithm, aren't we computing all these t's? Actually, no. The efficiency is achieved in Liam-Barsk algorithm by actually being able to break out of these four if conditions earlier. I mean, if we could have written these if conditions, for example, by computing, we could have computed all these visibles beforehand and assign them to some Boolean values. If we didn't have these if conditions and say A, for example, this one is whether it's so it's using X-min. L is this visible, R is this visible, B is this visible. If we just have four statements that return these things, it will be much less efficient because having an if ladder like this allows you actually, when it returns false, for example, you probably are going to avoid computing the intersection points for the other t values, as you can see. So here, in this visible, we are sometimes returning false, which allows us to break out of this if ladder early, which avoids the computation of the rest completely. For these are like trivial reject cases that we have. So really, we do computation necessary only when, I mean, the computation of the t values is only going to be done when we are satisfied. The first two ifs do not return false. That's the only case where we are going to compute the intersection with the bottom boundary. So all these things actually make it make this algorithm efficient to be able to break out early, to for example look at these intersection points, and if we see something wrong with these intersections, for example if this the current intersection is larger than when it's left the plane already, it's larger than TL, for example, that's the point. The line should be entirely outside the clipping window. So these cases where we understand the line is completely outside, we can break out early. That's the basic thing. And if you're not breaking out early, then we just update R. Instead of these sorting the t values at the end, we are just updating them on the fly as we find these new t values. So it's like we're shortening our line segment one by every t value as if we find something to update on to clip the line basically. Still, there are things that may be more efficient. For example, like the left, right, bottom, top ordering may not always give you for every line segment. This is not the most optimum ordering of the if ladder. Maybe there's a different if ladder here which will allow you to break out early for certain types of lines. Um, but yeah, finding those that's maybe more difficult than itself. I mean, when you're trying to make it more efficient, you may see that it's actually an overkill to do these checks. So basically, this is just what I wanted to note before we start today's lecture. The main reason here really is to find most efficient algorithm as possible, and sometimes there are new algorithms that come out, or sometimes the hardware becomes so good that the differences between, for example, an integer division and floating point division does not matter anymore. You have hardware accelerated, for example, floating point operations in which you can also divide the floating point numbers very fast. Or the gap between. It may still, integer division may still be a lot faster, but the developments in graphics hardware may reduce the gap between these things. So basically, these are the things that we try to optimize. Next week, for example, we're going to talk about a line drawing algorithm, which will be able to find the pixels that are affected by a given line segment given by two endpoints by just doing some integer additions and subtraction, no floating point operation. So that's something really interesting. So I mean, think about it as maybe if you have time during the weekend, think about it as a challenge. Can you figure out an algorithm in which I will be giving you on a grid. Here we have a grid. These are all pixels. Okay, this is an image with discrete pixels. I will give you some integer x1, y1 coordinate and an integer x2, y2 coordinate. and I want you to figure out, I want you to draw the find the pixels. For example, I go right, maybe I have to go up here, go another right here, another up. So can you figure out which pixels to highlight along this so that we will be drawing this line? I'm thinking just about binary. I'm not thinking about anti-aliasing, which is maybe having the neighborhood pixels with some grayish color, but I'm just thinking about white and black. If we have white background, if the line is going to be drawn as a black line, which pixels have to be made black? If we have these two xy's, x1, y1, x2, y2, which are just integer numbers, can we figure out these pixels along the way by just using integer operations, integer addition and subtraction, and nothing more? Okay, so this is what we will be doing next week, but just a heads up, just to show you that doing things efficient. We could have written this, for example, we can find the slope of the line, and based on the slope, for example, every time we can increment the coordinate as a floating point number and round it to the nearest integer to figure out the pixel. Okay, so we can use round function, floating point operations to draw the line easily. Yeah, can you get rid of the floating point operations entirely and just do it with integer operations, is what we will see next week, for example. All right, so let's continue with the polygon clipping algorithm. This is a Sutherland-Hodgman algorithm. The polygon clipping is more difficult than line clipping because we may have arbitrary polygons and like non-convex polygons like this, which may end up being, after being clipped, which may end up as two different primitives. For example, this single polygon that you see on the left-hand side may, after clipping, may become a triangle and a rectangle, or a triangle you may have before may become a quadrilateral at the end. So there may be different cases. For example, can you think about different cases where a triangle will be something very different? For example, if I have a triangle like this, so it may have 1, 2, 3, 4, 5, and 6. So it may become an hexagon, not a regular one, but a triangle may become a 6 vertex polygon, an hexagon. Okay, so it's there may be different cases. So we are going to see this Sutherland-Hodgman algorithm is an iterative algorithm. I mean, it just treats each edge of the polygon one by one, and a polygon is given to us as an ordered list of its edges. Okay, we cannot, if somebody gives you a polygon, or it should be given to you as an ordered list of its vertices. So let's directly jump to examples. So yeah, this one is another object which, after clipped, may become something arbitrary. We can do divide and conquer approach, which means that we are going to clip that against every clipping plane one by one, and during that time we are going to keep updating the polygon again, and so when you combine everything, for example, first clip against the right edge, and then we are going to clip against the top edge, then left edge, and then bottom edge. At the end, we are going to end up with the clipped polygon. So yeah, clip against the bottom edge, and then clip against the left edge, and that's it. After that, when we clip against the top edge, we get ourselves our clipped polygon. So how does it work? We are going to, for every clipping boundary, we are going to visit the edges of the current polygon one by one, by starting with the starting vertex. And for example, if they're every step, so if the vertices are ordered from v0 to vn minus 1 for an angon, what we're going to do is we're going to start with v0, v1, then we're going to process v1, v2, v2, v3, V3, V4. So we are going to go like this by visiting every edge, every pair of adjacent vertices along the polygon. And here, let me look at this. So this one is, so let me ask you, what here, this clipping boundary here, is it, obviously it's not the top or bottom boundary, is it the left boundary or the right boundary? This one. I mean, it's a very simple question, but yeah. So am I looking, but because I'm just seeing it something like this, it doesn't tell whether it's left boundary or right boundary. So I need additional information to understand whether it's a left boundary or right boundary. So actually additional information is given here. This part is inside, this part is outside. So it must be the right boundary, right? Because this part is the inside of the clipping boundary. So this is the right boundary we have here, and we see these four cases, and these four cases could be simply explained in other clipping boundaries as well, but there are four different cases in which, for example, when both of your vertices are inside, we're just going to look at the points. Every time we are looking at our edge, there may be these four cases that we are going to be handling. And based on that, we are going to update some of these vertices and output, we are going to remove maybe some vertex and output two vertex at the end. So actually both of them are, every time we are processing them, both of them are removed from our list. What we are outputting is will make the new clipped polygon. So for example, when we have VI and VI plus VI plus one like this, if both of them are inside, we just put to the output VI plus one. Okay, why is not VI put into the output? VI probably was put into the output in the previous step. Okay, that's why we don't put it into the output. So look at these cases. When both of them are inside, we add the second vertex. This is the first vertex, this is the second vertex. Let's just first vertex, second vertex, here first vertex, second vertex, first vertex, second vertex. Okay, so if both of them are inside, we add the second vertex to the output. If VI is inside but the second vertex is outside, then we find the intersection point. We add this VI plus 1 prime. We add this new one to the output. So the edge of the clip polygon is going to become this when we put this to the output. Again, here VI is probably already is in the output. In order to not duplicate vertices in our polygon at the end, every vertex is going to appear exactly once in the final output. So when I say add to output, the output of the first clipping against a particular boundary will be a sequence of vertices of the clipped polygon, which is clipped with respect to this clipping boundary. If both of them are outside, so in the previous case, for example, it could have been like this. For example, no, not like this. When I'm talking about previous case, it has to be something like this. So if this is VI minus 1, what happens is that this one was already added to the output, but when we add to the output, we don't continue with the updated clip vertices. So when we're clipping a polygon, we're just processing its already existing vertices. So VI plus 1 prime is not replacing an existing list. It's not an in-place algorithm. So we already have one polygon, let's call it polygon P, with some set of vertices from V0 to Vn minus 1. So we just process them from beginning to the end, not playing with any of the vertices if they're outside, for example. At the end, we produce an output polygon, let's call it PO, which is going to have a new set of vertices. So this different cases here describe what this output is going to be. So if, for example, in this case, this was added, VI prime was added to the output, but then in the next pair of vertices are these two. Both of them are outside. We add nothing to the output, okay, at this point, because we are going to probably continue with something like this, where this one is outside, this one is inside, just like this, okay? When VI is inside, Vi plus 1 is, when Vi is outside, Vi plus 1 is inside, we again compute the intersection point, and in that case, we add both this one and this one to the output, okay? Because in this case, for example, if we are continuing with Vi plus 2, Vi plus 2 is going to be added afterwards, in which Vi plus 1 is assumed to be already added. So when the first vertex is outside, the second is inside, we add two vertices to the output, the intersection point and the next second vertex. If they're both outside, we add nothing to the output. If they're both inside, we add the second vertex to the output. If the first vertex is inside, the second is outside, we just add the intersection point to the output. And that's the algorithm basically. Let's go over an example. Yeah, here's the example. So we are going to process the entire polygon in its entirety from V0 to V3 first only against the first clipping boundary, which is the right edge. Then whatever is output from this step is going to be put as a input polygon for the second step, where we clip it against, for example, the left edge or the bottom edge, whatever that fixed order you are following. So the initial order is V0, V1, so this is our initial polygon, V0, V1, V2, V3. So when we're clipping against the right edge, as you can see, V0 is inside, V1 is outside. So what do? We find the intersection point, V1 prime. So V1 prime is added to the output. So our new polygon after clipping starts with V1 prime. Okay, so that's the first vertex of V1, the new polygon. And after that, V1, V2. V1 is outside, V2 is inside, so we find the intersection point V2 prime, and both of them are added. Both V2 prime and V2 are added to the output. So 2 is a subscript, not superscript. Okay, then V2, V3. V2 is inside, V3 is outside. We find the intersection point, let's call it V3 prime, and only this one is added to the output. The output becomes V3 prime. And then V3 is outside, V0 is inside. I mean, it's outside with respect to the left boundary, but with respect to the right boundary, it's, as you can see, it's inside. So so this one is outside, this one is inside, which means that we find intersection point V0 prime. And whether you call this V3 prime or V0 prime, it really doesn't matter. I mean, it's just the intersection point, and we just label it with something. And we add both of them to the output, V0 prime. And the first thing that we started was V0, which actually added at the end. So the new polygon becomes this. Let's look at the new polygon. V1 prime, V2 prime, V2, V3 prime, V0 prime, and V0. So it completes. So this one is a complete polygon, as you can see, starting here. So our polygon becomes this after it's clipped against the right edge. Okay, so we give this new polygon to the new clipping boundary and continue like this until the polygon is clipped against all the boundaries. So the algorithm is really simple actually. All you need to do is remember these cases and what you're doing in those cases. So the entire algorithm is indicated here on this in these 4 cases actually, and which is not very difficult to implement. Any questions about this? So after right edge, we can continue with the bottom edge. So as you can see, this is our new polygon. When we are doing it against the bottom edge, again, we can start with, I mean, here it's the order is changed. As you can see, V0 is taken as the first vertex. So when it doesn't matter, after you have a list of vertices, you can just the order is important. For example, I could have written the same polygon as V2 prime, starting with V2 prime, V2 prime, V2, V3 prime, V0 prime, V0 and V1 prime. So you can wrap around. So it's just a cycle of vertices. Where you start at this cycle does not matter actually. So we would find the correct polygon if we put this V0 at the end, as the first step suggests. So it's not that important. But the ordering of the vertices is important. So we cannot just get an arbitrary permutation of vertices. It will give a completely, it may give us a non-simple polygon in which the edges cross each other. So in simple polygons, we don't have edges crossing each other, and we are going to just deal with such cases in our computer graphics course. And when we clip against the left edge, we get this V0 double prime, V1 triple primes, and finally the top edge. The same algorithm is exactly executed for this new set of vertices. Again, for example, we start with V0 double prime, V1 double prime. Let's look at this. V0 double prime, V1 triple prime. V0 double prime, V1 triple prime. Both of them are inside. Okay, so again, the points, the clipping boundaries are included within the clip window. So when they're exactly on the clipping boundary, they are actually clipping against the top edge. Both of them are inside against the top edge anyway. But if there was some point on the clipping boundary itself, it's also considered inside. So both of them are as inside. As you can see, all the vertices here up to this point, all of them are inside. So until we come to V3 prime, we just add the next vertex. As you can see, add V1 double prime, V1 triple prime, double prime, V2 double prime, V2 prime, add V2, add V3 prime, and here V3 prime is inside, this one is outside. That's the point where we find the intersection, which is this V0 triple prime, and we add that one only to this list. And this one is outside, the other is inside, in which we add both of the intersection points and the next previous point to the output. And that's it. And after we have this, what we can do is, since this is an arbitrary polygon, if our only primitives are triangles, if we're, imagine the only rasterization that we can do, we only have either a line drawing algorithm or triangle drawing algorithm. When we have complicated shapes like this, we may not be able to rasterize them with our triangle rasterization, triangle filling, or triangle drawing algorithm. So one thing that we can do is, this is called tessellation or triangulation, which is a specific version of tessellation. We can just subdivide it, and this problem is difficult by itself, but if our polygons have certain properties, this subdivision can be made very efficient. For example, if our polygon is a Y-monotone polygon, which means that starting from top vertex, if you always go down on the left or right chain. This we talk about this in our computational geometry course, which deals with some entirely different than computer graphics. But I just want to say that there may be efficient algorithms to subdivide our polygon into triangles. Then we will have this many triangles, which we will render them separately if the only thing we have is a triangle drawing algorithm. And yeah, this concludes the clipping, line clipping and polygon clipping. The slide 59 concludes both of the subjects. The rest, which we have a couple of slides, like 8 slides, are about culling. And culling means completely removing objects. And we are going to see 3 types of culling, which is the first one is view frustum culling, in which actually, when we are doing clipping, some of the objects that are completely outside are culled. Okay, so we actually, in our clipping algorithm, we are culling objects that are outside the canonical view volume. But sometimes, for example, if you're, for example, in a building environment, in a virtual building, there may be thousands of objects in the building in different floors. But since the floors are not transparent, a lot of the objects are behind other objects. So one thing we can do is, for example, this is called occlusion culling. There are, for example, the room that you're in, the walls of the room that you're in occludes all the objects that are outside. So if we can find all those, so there may be lots of objects in the next room which are within your viewing frustum, viewing volume, the canonical viewing volume we have. But if they're occluded by the walls of the room, but they are going to pass on to the next stages of the rendering anyway because they're inside. So things that are behind other objects, if we can find them efficiently and throw them out completely before proceeding to the next stage, this is called, for example, occlusion culling. Or objects, if you have solid objects, for example, like this phone or like this mouse here. If you have a solid object like this, for example, the solid objects, the camera cannot go inside, right? At a certain point, you can only see if the solid objects that you see here on the camera, on the screen, is made up of small triangles. You can, at any point, you can only see, for example, this is the bottom of that mouse, for example. You cannot see the top of the mouse. You can only see the top of the mouse when those triangles that make up the top of the mouse are facing the camera. For example, if we can figure out if the faces, as you can see this mouse object, all the triangles, if we have their normal vectors, we know that which are their front faces. First of all, let me tell you, if the front faces of the triangles that make up this mouse are all facing outwards, it's not possible to actually see these triangles from behind, right? I mean, since your camera cannot go inside the mouse, can you see the triangle that makes up the surface, the top face, for example? Imagine there's a triangle at the top face of this mouse. Can you see that triangle from behind? No, not possible, right? So one thing that we can do is to make, like this mouse may be composed of 10,000 triangles when you're rendering it. Actually, you can get rid of about half of those 10,000 triangles immediately by completely removing from your object the triangles whose backs are facing you. For example, when you're looking at the mouse from bottom, for example, the front face here that you cannot see right now, it's the front face is facing away from the camera, which means that you're looking, if you were to see this triangle, you would see its back. But since it's not possible to see its back, you cannot go inside this solid object, why not completely remove that triangle from our rendering list? So this one is called backface culling. And sometimes when you're playing first-person shooter games or other games, sometimes you may find there are bugs in games. For example, places where the person should not go. For example, if you go inside, there may be, for example, a room that you're not supposed to go in. Which means that the room is modeled as a solid object in which the walls should not be seen from behind. But as you go in, you may feel that immediately the back walls are not there. I mean, you can see the solid objects from outside, but as soon as you go in, you can see they disappear. Because you're trying to see them from the behind, and since backface culling is probably on at that point, it's like the object completely disappears. I don't know whether you have faced such situations in games, but yeah, it happened to me. I mean, sometimes sometimes you don't need to completely go inside, but if your avatar just peeks in some object that's not supposed to go there, I mean, immediately the unnatural things, an unnatural view may appear in which you're seeing things that are far away that you're not supposed to see. For example, this also happens. For example, like for example, even I think in Minecraft, for example, when you're falling, when you see. If you manage to fall from the bedrock in Minecraft, and if you look upwards to the world, for example, you see the world as it's not supposed to be. I mean, you're seeing faraway things. Sometimes that's the most part where you see, okay, I see the insides of these objects, I see different objects, but that's because certain triangles, when you're looking from behind, they are actually not in the rendering list. So you can only see objects that are facing towards you. So this is called backface culling. And you should not always turn this on. This is something that you can turn it on for specific objects. For example, if you have a house, for example, in which the house wall can be viewed from forward, from outside and from inside, you should not turn on backface culling for that house wall, because it can be viewed from both ways. Okay, so because the outward facing normals probably are always fixed for triangles. It doesn't go, for example, the front if you have a house, the walls are, if the walls are facing outwards the house, when you go inside the house, it means that you are looking at the wall from its back side, in which the normal of the wall still is facing outwards. Okay, the normals are not dynamic, that change. When you have triangles, the triangles are specified, the triangle primitives in computer graphics are specified by a fixed ordering of their vertices. For example, what I'm saying is that when you have a triangle like this, a three-dimensional triangle, you have to give a vertex order, and by default this ordering is done in counterclockwise to show you that the triangle is facing towards outside the screen. So if you see a triangle, and if it, for example, if this is like the wall of a house, and you see something like this is the part of a wall of a house, that this triangle, V1, V2, V3. Look at this. Which face the normal, I mean, where is this, the normal of this triangle is facing? It's actually facing inside your screen. It's facing outwards. I mean, since we're in a, let me do it like this, with just to show you that we cannot see this part of it. Now it becomes like more 3D, which means that this normal is actually going away from you towards the screen. Okay, I mean, if I just do not have these dotted lines, I mean, it could have been coming towards you. That's the problem with 2D projections. Okay, you cannot find these. So yeah, the site shared some link. Let me quickly go there. Yeah, like this. Yeah, look at this. You're some. I think you're inside some kind of a mountain or something, or a hill under, or maybe you're under the hill. I think this is like just this is that Minecraft thing I was talking about. This is exactly the same thing. I think this guy is falling outside the entire scene under the map. Exactly. When it's under the map, you see all the back faces, so it's really unnatural, and you're just seeing the things that can be seen from front. So this is exactly what I was talking about. Thank you, Said, for this nice example. So this is backface culling. I mean, so as I said, when we have these triangles, the triangle vertices are specified for each primitive in a fixed order. So each triangle has a fixed front and back face. So when you turn on backface culling, which means it's done like this, the view direction from our camera eye point to any point inside the triangle is computed. Actually, I have a figure for that. Where is it? Right here. So this is our eye point. So, and this is the view vector, and this is the normal vector of the triangle. So the normal vector is given as the counterclockwise. If the counterclockwise order of your vertices are given to you, the normal is facing this way. If you just use, again, by using your right hand rule, if you trace the order of the vertices with your 4 fingers, the normal vector is given by your thumb. So this is how we can understand which one is the front face. So if the same triangle, as you can see, the same triangle, now we are seeing that triangle, as you can see, V0, V1, V2, this way from the other side. If you have to look this triangle from the other side, the ordering would be, or maybe it's a little bit, it may be a little bit rotated. As you can see, this was V0, right? I mean, oh no, actually, we are viewing it, maybe it may be rotated. We are seeing with a different angle probably. And this may be, for example, an equilateral triangle. Because of the projection, we may see different angles here, but imagine this is a three-dimensional triangle. And it may be an equilateral triangle here with all the angles 60 degrees here. So when we are seeing the same triangle this time, the normal is facing this way. Again, by using your right-hand rule, if you try to use your four fingers to trace these vertices in their order, v0, v1, v2, you see that the normal vector is trying to, your thumb is trying to push through the screen. So in this case, as you can see, our viewing angle to any point within the triangle, we are going to form a view vector to any point in the triangle. We cannot just use our gaze. Gaze will not correctly give us back facing triangles. We are going to form a view vector to any point on the triangle. That's our v vector. And we are going to take the dot product. We are going to look at the angle it makes. If the angle it makes is, I mean, if the dot product is a positive number, okay, so it's going to be a back-facing triangle. Because if you look at the angle between those, as you can see, these vectors, you can move them. So they don't have specific positions. As you can see, this is the same vector. The angle between n and v is less than 90 degrees. When the normal is facing us and we are facing, if for example, if we have a triangle directly facing us and our view vector is the other way, the angle between them is exactly 180 degrees. Okay, so we are able to see the front faces of the triangles when the angle between the normal vector and the view vector is larger than 90 degrees. So when it's larger than 90 degrees, the dot product between them is going to be a negative number, which means we are facing that triangle. We are seeing a front-facing triangle. Okay, so if the dot product is, if the angle between them is, and if you're facing the same direction, for example, if your triangle is exactly, this front face is exactly away from you, which means that it's exactly alongside with your viewpoint, like this, the angle between them is 0 degrees, the dot product is 0, you're not, sorry, the dot product is going to be 1 at that point. Cosine 0 is 1. So dot product gives us the cosine of the angle, which means that when it's 0 degrees, that's the largest the dot product is going to be, which is 1. So we can find for all the triangles in our scene, this is not a very difficult operation to perform, the dot product. We can compute the dot product and completely remove, for solid objects, we can completely remove the triangles that are not facing us. So actually in games, for example, if you have a mouse like this, the mouse actually, for the computer graphics system, the mouse is something that doesn't have a backside. All these faces that are not facing you, they are actually taken out. You don't see them, but it doesn't cause a problem, right? And you don't see them, their non-existence is no problem. So it's like a philosophical statement here, but that's what computer graphics uses, a philosophical statement. If you don't see them, whether they exist or not, doesn't matter to you. So it's some kind of an existential problem for computer graphical objects, but that's the case, unfortunately, for them. If you don't see them, it doesn't matter whether they exist or not. Okay, so that's those are the three. So I talked about backface culling, occlusion culling, and there's also view frustum culling. Actually, here the clipping and culling part, the parts that were completely rejected, the lines that are completely outside the canonical view volume, are actually view frustum culled. But there's also other. It says there's no OpenGL support. I'm actually confused a little bit at this. If that clipping and culling is part of the pipeline, why do we say there is no OpenGL support? I mean, if we did clipping and culling, I mean, if we did clip for example, if we use the polygon clipping algorithm to completely, doesn't it completely remove a polygon that is outside our canonical view volume? Let me, so honestly, I don't know the question to this right now. I will talk about this maybe on Tuesday, but that's a little bit confusing to me. How this view frustum culling is different than this view volume culling is different than the clipping window, the canonical view volume we had to clip our lines and to clip our polygons in with the Sutherland-Hodgman algorithm or Cohen-Sutherland Liam-Barsky algorithm. So for example, if I have a set of line segments, doesn't Liam-Barsky algorithm do view frustum culling by removing all the lines that are outside the viewing volume? Okay, so this is the removal of geometry outside the viewing volume. That's the same thing with it in line clipping. Obviously I'm missing something here. Okay, so I'm going to take a look at this for next week, but I tell you the difference between the clipping and culling stage in the pipeline and this view frustum culling that we talked about here. Probably it's also written in this Lighthouse 3D tutorials as well. Okay, and probably somebody also asked the same question in those graphics forums, so I'm going to find the answer. But if you know the answer, if anybody knows the answer already, I will be happy to hear your suggestions. But yeah, view frustum culling is very similar to what we have done in canonical view volume in clipping and culling algorithms. So here we have the plane equation, and and we have if any plane, the vertexes, we can identify whether a vertex is outside or inside by with this simple test with the polygon. If all vertices are outside with respect to the same plane, then the primitive is outside and can be called. I mean, this is like our trivial reject case, right? So we already did this in Liam-Barsky algorithm. I think what this view frustum culling can talk about, I think here the difference that I guess is to completely remove an object that is composed of, for example, 10,000 triangles. Okay, imagine you have an object which is composed of 10,000 triangles. If you have those 10,000 triangles proceed to the clipping and culling stage, each of those 10,000 triangles are going to be clipped one by one. But view frustum culling is about understanding the entirety of your object is outside your scene, and do not, for example, draw that mountain or avatar or that house completely. Okay, so this is like we're thinking about not at the primitive level, but at the object level. Can we completely throw out the entire object with its all 10,000 triangles completely? That may be the difference here. So, using a bounding box, if you use a bounding box and bounding sphere and determine that the entire object is outside, and do not call its, do not send any of its primitives to the subsequent stages of the pipeline, may be the difference between this view frustum culling and the clipping, the algorithms we have seen previously. Because in clipping algorithms, we did not remove entire, we just dealt with primitives, lines and polygons. Here with view frustum culling, I think you do it instead of sending each triangle to the clipping stages or clipping culling stages, you completely remove an entire object with thousands of triangles. And backface culling, OpenGL supports backface culling. So graphics libraries, our forward rendering default pipeline supports backface culling. It's something you can turn on and off. And there are some interesting things too. You can actually do front face culling. For example, you can render this object by making a setting which is really unnatural, but you can say that cull, remove all the faces that are facing the viewer, front faces, and render everything that are back face. So it's like we are going to be seeing the bunny from inside. So it's going to just imagine you're not seeing these faces, but it's like the bunny is cut out and your camera is inside and you're seeing the faces that are whose backs are facing you. That's called front face culling. If you set this cull face parameter to be GL front, the front faces, and when you enable this setting by saying GL enable GL cull face, you can get this happening. And the most obvious, the default thing to do is the natural thing to do is to call back faces, and by just calling these two functions in your init function, or just the initial calling these functions before you're drawing a solid object, you can enable backface culling. And this is, by the way, we're out of time, but we're also almost out of slides, so I'm going to continue and quickly finish the remaining set of slides. In backface culling, what we do is we're not just using the gaze vector. As you can see, the dot product between the gaze and normal here is less than 90 degrees, so it's a positive number, but it's not backface. We're actually using this view vector with the normal vector, and the angle between them in this case, as you can see, is greater than 90 degrees. So it's a front face that we can see. Okay, and the angle here between them is less than 90 degrees, as you can see, and if this is the normal, it can be called. It should not be called. So we are not using, so this is a side note, we shouldn't just use the gaze vector minus W to do the dot product with the normal vectors. Let me now go to, oh, I didn't clear them. Okay. And there's also occlusion culling. I briefly mentioned that. We're not going to go into the details. There is a hidden slide here, which we're not going to cover, and it's not in your PDFs. But it's the OpenGL. It's possible to do occlusion culling in OpenGL with a complicated set of steps. So we're not going to cover that here in this class. But the idea is basically, if things are behind other objects. By the way, when things are behind other objects, we're not going to see them anyway, right? I mean, it's just like the difference between clipping Liam-Barsky algorithm and view-Frustum culling of complete objects. Here, when the bunny is behind this large triangle, in our final image, we're not going to be able to see the bunny behind this large triangle, but in culling, the purpose is to completely remove the primitives of this bunny to proceed to the further stages of rasterization. So because after rasterization, or at the point of rasterization, we are going to figure out that, oh, some of these triangles are behind here, so they will not be allowed to update the pixels on our image. But if we try to render these, if you don't call them, it takes a lot of time to rasterize each of these triangles and finally figuring out, oh, they're behind some triangle and they cannot update the image. At the last step is an unnecessary time that we have spent to render those triangles. So the purpose of occlusion culling, which can be used to speed up your graphics applications a lot, is to figure out which objects are behind certain objects beforehand and completely remove them. Okay, it has, with a fast rendering pass, OpenGL actually allows you to figure out certain objects that are behind really fast. This is used in games to speed up the rendering process. But we're not going to. It's a complicated. If you wonder about it, you can send me an email, and I can, or you can find on the internet how occlusion culling is done in OpenGL. So it supports certain functions that allow you to do occlusion queries and do occlusion culling, but or you can have different data structures and algorithms yourself. For example, if I have an indoor game in a building, if I'm in a room, I can completely remove objects that are outside the room, for example, by using something like a BSP tree, by using binary space partitioning, and for example, using the voles as dividers in my binary space partitioning tree. While I'm traversing the binary space partitioning tree, I can cull the objects that are behind voles immediately with no intelligent thing or any geometric operations that are needed. Actually, this was done in the early games, in the early first-person shooter games, like Doom, or Quake. The occlusion culling was done this way by using binary space partitioning trees. But there are other ways to do that. But the important thing here from occlusion culling you should know is completely removal of objects that are going to stay behind other objects for sure. Okay, and this one, as the camera moves around the scene, you have to compute occlusion culling at every frame. Or when you go, for example, outside the room, as objects that are outside the room are now going to be visible. So this is not something you can do at pre-processing in one pass. You have to do occlusion culling dynamically as your avatar or as your camera is moving in the scene. Okay, that's it from me for today. And this concludes our clipping and culling slides. We are going to continue with rasterization, line drawing, that simple exercise that I gave you. How do you do line drawing with just integer addition and subtraction? We are going to see those algorithms and how to interpolate colors along triangle surfaces next week. And that's part is called rasterization. Okay, and that will conclude the forward rendering pipeline. You'll have another algorithm to have render virtual scenes. Let me stop recording now.